Good morning to everyone. Today we're going to be looking at, I think it's a little bit more of a difficult lesson, so you're going to have to really make sure that you're following along and writing down all the notes and doing all the examples together with me. There are several examples you're going to notice on your lesson sheet that the entire first page is nothing but notes. I'm going to do a few also just on my whiteboard for you to see that you do not have to take notes on. So I'll make sure to let you know when I want you to write down what I'm writing and when I'm just showing you another example off to the side. You're also going to notice when you're looking at the problems, there's only 10 problems that I'm assigning to you today. That is because we are writing so many notes. But the lesson is still going to be worth 15 possible points. So you're going to want to make sure that you do a good job on taking notes, because there's 10 problems, so I'm adding 5 points just for the notes. So when you send me your lesson problems, please make sure that you're sending your notes along as well, because you want to make sure that you don't lose those 5 points that are going to be part of this lesson. Okay, so let's go ahead. I'm going to start off with an example down here at the bottom. You don't have to write what I'm writing right now. I'm just going to kind of run through what a probability problem, where we're looking at two different events, how that actually works out. We've actually done probability problems in the past, but they've been a little bit more simple. And I can think of one right off the top of my head. Might have been something like, if you have a bag of marbles and there's 3 red marbles inside of it, and there's 2 blue, and there's 1 white. What is the probability that you would draw out 1 blue marble when you reach in the bag and don't peek? Well, that would be 1 out of whatever the total is here, so we have 6. So your chances of pulling that blue marble out would be 1 in 6 chances. That's the probability, 1/6 or 1 in 6. Okay, so we're going to be looking at something like that, but we're kind of stepping it up a notch. So let's kind of get this example down here so you can see what we're going to be working about. Okay, what we're going to be working on rather. Okay, so let's say that the probability, we're talking about a coin, a 2-sided coin. We have heads and we have tails. So the probability of getting heads on one toss of a coin would be 1 out of 2, right? So we would say, just as an example, so say we have this coin. Say we have this coin, it's a dime or whatever, 10 cents, and it's heads on one side, and we know that it's tails on the opposite side. So when you flip this thing, then you toss it, the chances of getting heads would be 1 in 2, because there's 2 sides to the coin. The way we say that and write that is the probability that I would toss the coin and get heads is 1 in 2. Okay, or 1/2. But that's how we write it, and we say probability of heads. So you're going to see us writing problems like that all throughout the lesson. So the probability of getting heads on the second toss of a coin is also 1 in 2, right? I could toss that thing all day long. The chances of getting heads each time I toss it is still going to be 1 in 2. That's not going to change, okay? But let's say I am talking about 2 tosses. So the probability of getting 2 heads in a row, so I toss this thing 2 times, okay, and the chances of getting, or the probability of landing on heads both times is 1 in 2 and 1 in 2. That's how we figure that out. So the chances of getting heads on both tosses is actually 1 in 4. Now we're going to talk more specifically about that. Let's go back up here now to your notes. I want you to look up in the upper left-hand corner. This is probably a good time to go ahead and fill in what an independent event is. So an independent event, let's go ahead and write that. The probability of independent events occurring in a specified order is the product of the probability of the first event and the probability of the second event. Notice the words in here. Product means multiply, right? Okay, so that's what I did down here. I multiplied my 2 events. This was the first toss, and this was the second toss. There are two events, we call those. When I threw the coin up once, that's my first event. When I threw it up the second time, that's my second event. And according to what an independent event is we multiply the first event times the second event. Okay, so that's just kind of a starter here. Now, I can illustrate this very thing using what's called a tree diagram. I could say this represents my first event. I'm going to flip the coin. It can turn out to either be heads or it could be tails. Okay, that's the first toss. If the first toss comes up heads, I'm going to draw my tree out this way. If I'm considering the fact that when I flipped it, if it came up heads, and now I'm going to work on my second toss, that could also be heads or tails, right? My second toss. What if on my second toss, what if my first toss was tails, and I'm going to toss it a second time? My second time could also be heads or it could be tails. Okay, so what I see here is I've got 4 different possibilities here. And actually, I like to say that a different way. Equal possibilities. I have 4 equal possibilities here. It could be any one of those combinations. So I'm going to off to the side over here. I'm going to write down off to the left. I'm going to write what all of those possibilities would be. So I could have tossed it and got heads on the first toss and heads on the second toss. I could have gotten heads on the first toss and tails on the second toss, or I could have gotten tails on the first toss and heads on the second toss, or I could have gotten tails on the first toss and tails on the second toss. Okay, so there's 4 possibilities here. But the only one that we're after is remember what the problem was what was the possibility of getting heads on the first toss and the second toss? So this is really the combination that we were looking for, and that is 1 out of 4, right? Because there's 4 total combinations or equal possibilities. And notice this answer actually turns out to be the same as that. So if I take the tosses, each toss, and I record those like so, my first toss was 1 and 2, my second toss was 1 out of 2, and we multiply those for a product of 1/4. So the answer to that then would be 1/4. And that's just kind of a simple illustration to show you why it actually works, because we're not going to show the why from here on out. From here on out, we're just going to do the work as we are instructed to do it, meaning that we're going to find the products of the events. Okay, we call the list of outcomes, by the way. Let me just show you that really quickly. So when I had heads, or heads, I'm going to write them across this way, heads, tails, tails, heads, or tails, tails. On those 4, when we looked at those 4 possible outcomes, we call these a sample space. You don't have to write that down. I just want you to kind of make a mental note of it. Okay, so let's see. How would we express that problem that we just figured out where the answer was 1/4? Here's what we would say. Remember that we mentioned that we actually say the probability of heads. In this case, we say the probability of heads, because that's what we were looking for, was to toss the coin twice and get heads on the first toss and heads on the second toss. So we label here what it is we're actually trying to get, and then we say what the probability is 1/4. And that would be the answer to that problem. The probability of heads is 1 in 4. Okay, now why is this called an independent event? An independent event, it's called that because the outcome of the first event does not affect the outcome of the second event. Think about it. I toss the coin once, whatever I want, it's going to either turn up heads or it's going to turn up tails. I take the coin again, I toss it, and I'm going to have the same opportunity or the same possible outcomes. I'm going to have 1 and 2 chances of getting heads or tails. right? But what happens on this event has no reflection on what happens on this event. It's the same coin. We're tossing it a second time, but the events don't affect each other. They're separate events. And you'll see how that really works when we talk about dependent events in just a few moments. Okay, I'm going to go ahead and erase this off in case I need to use it again. All right. Now, I am going to see here. I'm going to show you some examples here of some more independent events that are occurring in a specified order. So let's say we are looking for, here's three examples we're going to look at. Let's say we're trying to figure out the probability that when in the flip of coin, when we're flipping a coin, that it would turn out to be heads the first time, heads the second time, and tails the third time. So what is the probability that I flip that coin 3 times and it turns up to be heads, heads, and tails? Okay, now let's just look at this for a minute. How many equal possibilities are there actually? If I do the math that I just said we would use, I would say, okay, well, the first toss is going to be, what's the chances of me getting heads? 1 and 2, right? How about the second one? The same thing, 1 and 2. How about the third toss? 1 and 2, chances that I'm going to get tails. If I multiply those, then I would say that it's 1 in 8 chances that I would end up with this combination right here when I toss that coin 3 times. That is the answer to that problem. But now let's look at, I'm going to show you one more time. I said I wasn't going to do it, but I just remembered in my notes, I actually wrote off to the side that I wanted to use this one to show it to you. And then from here on out, I won't show this any longer. Okay, so I'm going to actually write out all the possibilities that we could get when we toss that coin 3 times. Okay, so the first time it could be heads, second time it could be tails, third time it could be heads. The next time it could be heads, heads, heads. Another possibility would be heads, heads, tails. Another possibility, which is what we're looking for, right? So I'm going to kind of star that one. Another possibility could be heads, tails, tails. Another possibility could be tails, tails, tails. We could also get tails, heads, tails. We could get tails, heads, heads. Or we could get tails, tails, heads. And I think that's all of them. And that's 1, 2, 3, 4, 5, 6, 7, 8 different equal possibilities. But this is the one we're actually after. So what are the chances that I could flip that coin 3 times and end up with heads, heads, tails? Is 1 in 8. Do you see that? Because there's 8 equal possibilities, and I'm only looking for this one. So it's 1 in 8. Now notice here how the math turned out. It turned out perfect by multiplying each one of those events, the probability of those events. Okay, so that is accurate, and that is how we're going to find the probabilities from here on out. So let's go on up to our notes now. I'm going to have you guys go up to example 1. Example 1, we have the face of a spinner here. It's divided into 4 congruent sectors. The question is, what is the probability of getting a 2 on the first spin and a 1 on the second spin? So first of all, let's write the probability of, what did we say, 2 and 1? Of spinning a 2 and a 1 in that order. Okay, so I'm going to spin it twice. What's the probability of getting a 2 the first time I spin it and the probability of getting a 1 the second time we spin it? Again, this is definitely an independent event because each time I spin it, there's no effect from one event to the next. I can spin it all day long. There's separate spins. What I do on the first spin has no reflection on what happens on the second spin. Okay, so what is the chance, or what is the probability of spinning a 2? Well, there's 4 sectors, so there's 1 in 4 chances that I would land on a 2 the first time. And then what about the 1? Spinning a 1 would also be 1 in 4 chances, right? The probability is 1 in 4. We multiply those and we get 1/16. So the probability that I would spin a 2 and then a 1 would be 1 in 16 chances. Example 2. Jim tossed a coin once and it turned up heads. What is the probability that he will get heads on the next toss of the coin? So really, we're not talking about the probability of the first toss because we are already told that it turned up heads. We're only talking about the next toss. So what would that be? What's the probability that he would toss that coin and get heads? Well, there's only two sides to the coin. So the answer to that would be 1/2 or 1 and 2. Third example, if a pair of dot cubes, okay, we're talking about like dice. If a pair of dot cubes is tossed once, what is the probability that the total number rolled will be 12? Okay, now let's think about this. If the total number has to be 12 and there is a pair of dot cubes, we're only tossing it once. What's the probability that the total number will be 12? Well, what does that mean about each one of those dot cubes? What would it take for the total to be 12? If I rolled a 1, could the second dot cube roll any number that would make the total 12? No, I don't think so. So we're going to make a little note right here that both of those dot cubes must be a 6, right? That's the only combination of those two dot cubes that when you roll them would give you a total of 12. They both have to turn up to be a 6. So let's write this down. So what is the probability that I would roll a 6 and a 6? So we're going to use what we've been learning. So if we get a 6, that's going to be 1 in 6. That's the first event. What about the second event? The second roll, we multiply it. To get a 6 would be 1 in 6. What's the probability you would roll a 6? 1 in 6. Let's do our multiplication. We get 1 in 36. So the probability that you could have a pair of dot cubes and you toss them one time, the probability that you'll get a 6 and a 6 is 1 in 36. Isn't that interesting? All right, example 4 is a little bit longer. I kind of put it on two sides here because we're going to look at two different methods for this. All right, so here's the question for example 4. With one toss of a pair of dot cubes, what is the probability of rolling a total that's greater than 9? Okay, so I hope that when you printed your lesson, this chart over here of outcomes did not turn out blurry like it looks here in my lesson that I'm showing you here. Yours should look a little bit better, but you can still make this out, I think. Okay, so let's think about this. So with one toss of a pair of dot cubes, what is the probability of rolling a total greater than 9? So we have to put some thought into this. But I'm going to show you what this little outcome chart over here actually means. And this is not actually called, I wouldn't call this an outcome chart, even though that's what it says. The outcome of the first dot cube is what's across the top, and then across the side is the outcome of the second dot cube. So if I rolled this and this, I would get this. Okay, so what they're showing is the two dots that are being rolled together. All right, this is called a sample space. And we talked about that a little bit earlier. But this is a sample space. So let's think about this. So if I could roll, I tossed a pair, so I'm tossing two dot cubes, what is the probability that I would get a combination or a total that's greater than 9? So let's go find, first of all of these numbers that are in here are when it's like a multiplication chart kind of, but that's how you follow it. So when you roll, for example, if I roll a 6 and I roll a 4, I get a 10. Okay, so that's how I want you to think about this as I'm going through here. So let's find all the rolls or all the tosses that produced a total of a number that is greater than 9. So we have all those 10s, there's a couple of 11s, and then when you roll a 6 and a 6, you get 12. All of those numbers are greater than 9, and that's it. So let's, first of all, the question number 1 is asking us to determine the total number of combinations. So what they're asking you there is when you have all 6 dice and you've rolled them, if you rolled them all together or you rolled them 2 dice at a time, or 2 dot cubes at a time, what are all the possible combinations you can get? It's what you see on this entire chart, and there's 36 of them. So there's 6 across, 1, 2, 3, 4, 5, 6, and there's 6 down, 1, 2, 3, 4, 5, 6. Okay, so there are 36 total combinations that could possibly be rolled. Okay, number 2, we're going to count all numbers that are greater than 9. We're going to start right down here. How many 10s could be rolled? 3. How many 11s could be rolled? 2. How many 12s could be rolled? 1. Okay, so that total, we're going to write this little word right here. We're going to add these up, and we're going to get 6 right here. So all the numbers that are greater than 9 in my sample space, there are 6. So the probability that I would roll a number that's greater than 9 is 6 out of 36 chances. I can reduce that, and that becomes 1 in 6. And that's the answer to that. So now we know, even though we're going to be looking at another method over here, we're going to get 1/6, but I want to show you how to actually work that out so that you'll have an understanding of how we can do that, because you might not always have a sample space that looks like that we just used. So method 2. So first of all, we have to think each roll is an independent event. Okay, and in order to roll a number that's greater than 9, we have to consider all the equal possibilities. So I'm going to start right here. I want to think to myself, okay, if my first roll is a 1, what could I roll that would give me a total number that's greater than 9? Well, since the largest number on a dot cube is 6, if I rolled a 1 and a 6, I'm only at 7, correct? So 1 isn't even applicable. How about 2? If I roll a 2, what can I roll that would give me a number greater than 9? Well, again, if 6 is the greatest number on a dot cube, if I roll a 2 on the first roll and a 6 on the second roll, that's only 8. That's not greater than 9, so that doesn't work either. How about the 3? If I roll a 3 and I roll a 6, I'm at 9, but we're looking for something that's greater than 9. So 3 doesn't work either. So actually, all 3 of these are not possible. There's no possible outcomes for the first roll to be a 1, 2, or 3. It cannot happen. Okay, so now let's talk about, what if my first roll is a 4? What must my second roll be? Can't be a 4 because that'd be 8. A 5 would be 9. So therefore, it needs to be a 6. Okay, so we're going to write down here, this is our first roll. If our first roll is a 6, if our first roll is a 4, our second roll has to be a 6 in order to produce a total that's greater than 9. So how do we do this? We're going to take the first event is 1 in 6 that I'm going to get a 4. What were the chances of me rolling a 6 on the second one? 1 in 6. So I get 1 in 36. I'm going to go ahead and I'm going to circle that. Let's talk about, what if the first roll is a 5? We're down here now. If the first roll is a 5, then the second roll may be what 2 numbers? Remember, whatever the second roll needs to cause you to have a total greater than 9. So 5 and 4 is 9, so it can't be 4. So it has to be a 5, or it can be a 6, right? So it may be either one of those. So how do we write that? So here's how we do that. So the probability that when I roll a 5, if my first roll is 5, in order to produce a number that's greater than 9, my second roll may be either a 5 or a 6. But remember, this is just my second event. The 5 is my first roll. My second roll can be either a 5 or a 6. So how do I handle that? Well, the first event, if I roll a 5, what are my chances? 1 in 6. My second event can be 2. And the question is, what is the probability that on my second roll or my second toss of the dot cube, I'm going to get a 5 or a 6? Well, my chances then would be 2 out of 6. So now I can multiply that, and I'm going to get 2 out of 36. That can be reduced, but I'm going to leave it as a 36, and I'll show you why in just a moment. So please leave that as a 36. All right, now, let's look at this one down here. If my first roll is a 6, then my second roll may be what? It has to be greater than 9, so let's think about this. So 6 plus 3 is 9, but it has to be greater than 9. So if I roll a 6 on the first roll, let's go ahead and write this down here. If my first event rolls a 6, then my second roll may be a 4, because that would give me 10, right? A 5 or a 6. Because if I roll a 6 on the first one and I roll a 5 on the second one, that gives me a total of 11, which is greater than 9. If I roll a 6 on the first roll and I roll a 6 on the second roll, then I have a total of 12, which is also greater than 9. So we write this as the probability of 6 and 4, 5, and 6. And that is all considered my second event. So the 6 is the first toss. So what was the possibility of me getting a 6 on the first toss? We've already identified that's 1 and 6. Now, think about these 3 numbers here. That's the second roll. It's only one event. So the possibility when I roll that dice, what's the possibility of me rolling, or the probability of me rolling a 4, a 5, or a 6? That's 3 different numbers. There are 6 possible numbers that I could roll. So in order to get a 4, 5, or 6, it would be 3 out of 6. I do the math here, and I end up with 4 over 36. So 4 and 36. That would be the probability of rolling a 6 and then rolling a 4, a 5, or a 6. Okay? And then finally, we add all 3 of the numbers that we have boxed in there. So I'm going to take from my first one here, my second one, and my third one. I'm going to add those together. 1 over 36 plus 2 over 36 plus 3 over 36. And, oh, excuse me, that's a 4. Oh, no, it's not. Sorry, guys. That should be a 3. Whoopsie. Hopefully you guys caught me. What did we say here? That's not a times. There we go. That's better. And I end up, if I add those, I have 6 for my numerator, 36 for my denominator. I can reduce that to 1/6. The long way, yes, but probably an important method to understand, okay? But notice we got 1/6 here and 1/6 here, but we won't always have the beauty of having this sample space. Okay, so sometimes we're going to have to look at method 2 and know how to work that out. It's really just kind of an organization of your thoughts and considering what each event's possibility could be. Okay, now we're going to talk about dependent events. And we're going to start off with, let me see here. I had to write a lot of notes for this particular lesson. Okay, so I'm going to we're going to write down what dependent events are first. So let's go ahead and fill those in. The probability of dependent events occurring in a specified order is the product, so far it's pretty much the same, of the first event, but this is where it gets different right here, and the recalculated probability of each subsequent event. Subsequent means each event thereafter. So I'm going to go down to the bottom of my document here. I'm going to erase what I had, and I'm going to show you an example here that's dealing with a dependent event. Okay, so here's the problem. Let's say we draw a card from a deck. Let me find this in the book and I can read it right to you. Okay. Hold on one second, because actually I have this one going into our notes. Yeah, actually, I thought I had one I was going to do before I gave you the one I wanted in your notes, but it looks like we're going to go right to our notes. So I'll do another one later. Let's go right up here to example 5. We're going to look at this one together. Okay, example 5 says, from a well-mixed deck of cards, Josephina selected and kept one card, then a second card, then a third card, and finally a fourth card. What is the probability that the 4 cards Josephina selected are aces? All right, so here's what we're looking to find. The probability that each time she pulls a card, she gets an ace each of those 4 times. So there's the probability of drawing 4 aces. An ace on the first draw, an ace on the second draw, an ace on the third draw, and an ace on the fourth draw. Here's what makes this a dependent event. I want you to think about this. It says each time she pulled a card, she kept it. She did not place it back in the deck. So that first event, so let's talk about that. So she's got a deck of 52 cards. When she pulls out that first card, what's the probability that she's going to pull an ace? There's 52 cards in a deck. Okay, so there are 4 aces in a deck, and there's a total of 52. So for her chances on that first event of pulling an ace, she has 4 chances out of 52 to pull that ace. The second one, now we're still going to multiply. The second event is now affected by the first event because now there's only 51 cards in the deck. She's not placing the card that she pulled out. She's not putting it back into the deck. She's holding it out. So the probability of the second event is affected by the first because there's less cards in the deck. Okay. Also, it's going to lessen the amount of aces that could possibly be in there because what if she did pull an ace out on that first pull? So her chances now on the second event to pull an ace are 3 out of 51. So watch how this is going to work. Now there's 50 cards, and she has 2 chances to pull an ace out of 50. And now, finally, on the fourth draw, there's 49 cards, and she has the probability that she pulls the fourth ace is 1 in 49 chances. Now, these are some big numbers here, and you might not be able to recognize that we can cross-cancel some of these, but we can. So let's see, 4 goes into 52 13 times. 3 goes into 51 17 times. 2 goes into 50 25 times. This is a humongous number, and I'm going to give you a wonderful gift here. This equals, of course, when we multiply the numerator, we get 1. Watch how huge this number on the denominator becomes. 270,725. So she has 1 chance in 270,725. That's not very, the probability of her pulling an ace on each one of those times is not, it's pretty slim, slim chances to none. Okay, so that's the answer to that example. Okay, let's see. Okay, I'm going to just go back down to the bottom, and then we'll come back up here and do example 6 in just a moment. So let's look at another one together. Let's think about this. What if, let me find the problem in the book here. Okay. Suppose you're going to take a 10-question true-false test, a 10-question true-false test. Instead of reading the questions, you decide to guess every single answer. What is the probability that you're going to guess the correct answer to all 10 questions? So let's think about this. So how many events are there going to be? how many questions are there? There are 10. So there are 10 events. Are they dependent or are they independent of one another? Let's think about that. What you answer for the first one, does that affect the second event? What you answer for the second event, does that affect the third event? No, they're all separate events. So these are independent events. Okay, these are just some important things to think about. Okay, so what are the chances on the first question that you're going to answer the correct answer? It's either true or it's false. So you have 1 in 2 chances, right? What about the second question? 1 in 2. These are independent. So actually, you've got 10 questions. You're going to write this thing 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But a better way to write this might be using an exponent. 1/2 to the 10th power means I'm going to multiply 1/2 10 times. Remember too, because the book actually shows it like this, so I want to make sure you know that what this means. This means exactly what we wrote up here. Okay, it's not, you have to have the parentheses, because if I don't put the parentheses, here's what I'm saying. I'm only raising the 1, my numerator, to the 10th power. So you have to be careful that when you're writing this, all of this as an exponent, that you include the parentheses. Also, think about this. So what it actually means then is I'm raising the 1 to the 10th power and the 2 to the 10th power, right? Because look up here. All these 1s are going to be multiplied. That's 1 to the 10th power. We know that's 1. And 2 to the 10th power, because I put it into my calculator, is 1024. That's a lot to sit down and try to figure out. Something this big, it is helpful to just put it into your calculator. There are keys on there that allow you to, it's on the scientific calculator, although I have to tell you that sometimes on your phone, and you can try this, you can see if you can find it, turn your cell phones sideways so you can go to the calculator, turn it sideways, and you'll see the scientific calculator will pop up. And if you will key in for this part to get that number, you would need to key in a 2, and then you have to look for the key that says something like this. It'll be Y to, I don't remember how, I can't turn, I don't have my phone sitting here with me, but it might be like to the X, or it might be X to the Y. So they're letting you fill in an exponent that you want to use there. So hit 2, find that key that's got 2 variables here for your base number and for your exponent, and then put in there 10 equals, and it should give you 1024. Okay, so that would be the answer to that. So you don't have a very good chance of doing very well on this test if the chances that you're going to answer all 10 questions correctly is 1 in 1024 chances. Probably not going to do so well. Okay, so that's that one. Now we're going to go back up to the top and do a few more notes. See where we are here. Example 6. Okay, example 6 says we're going to, now this is a humongous one. So if you do have a calculator there, you can try this. We're going to find the probability of correctly guessing the answer to every question on a 20-question, 4-option, multiple-choice test. Okay, so how do we figure this out? Well, for each question, there's 20 questions, right? And each question has 4 possibilities. So that would mean that on the first question, what are the chances that I'm going to, what's the probability that I'm going to come up with the correct answer? Is 1 in 4, right? So there's 20 questions. So rather than writing 1/4 times 1/4 20 times, I'm just going to raise it to the 20th power here. This is not some kind of math that I want to do on the side of my paper. So yes, I would use my calculator. Now the book tells me that a scientific calculator may give it to you in the form of, the denominator will be in the form of scientific notation, but I don't have my actual scientific calculator here at home. It's still at school. So I did have to use my phone, and I also used the one on my computer, scientific calculator, and it did not produce it in scientific notation for me. It gave me a number that looks like this. 1. Here's the chances. If you just guess on a 20 question multiple choice test, your chances of getting them all right are like unbelievably small. So let's see here. It's 1,099,511,627,776. That is your chances of doing well. This written, the book tells us it should come out on your calculator like this. If you actually have an actual calculator there that gave it to you, it should have come out like this. Now I look at this and I think I'm going to have to go get my decimal point right there. So I'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I would think you'd write it like this. Right? And it would be times 10 to the 12th power. But in the book, they must have rounded this right here to 1.1, because in the book, they're telling us that it would come out on your calculator like this. That's a 12. Okay, so that either one of these are acceptable answers. But the truth of the matter is that the probability of correctly guessing all 20 answers is less than 1 in a trillion. So my advice to all of us would be to study for that test. Don't you think? Okay, and that completes the notes for today. That was a lot of notes. It's kind of a fun lesson, I thought. When I first read it, it was so much reading that it actually was a little bit difficult, and it's been a long time since I've seen this. So, and last year we didn't get this far in the book. So this was a little bit new to me, really, after several years of teaching it. So I really needed the refresher. But once I went through it a couple times and wrote my notes, it really came back to me. So honestly, if you just think through it, envision yourself being the person rolling the dice. Envision yourself as being the person pulling the card from the deck. I gave you one problem, I believe. Let me double check. In the lesson from 94, I did. Number 11 is coming from this lesson. I did not grab many. I actually went through the problems that I'm assigning to you today are a mixture of a few from these most recent lessons, and then mostly, if there were some there that you're going to see similar problems on the next test, those are the ones that I chose for you to do. So, alrighty guys, there you go. If you have questions, again, Edmodo is the best place to get me. You guys have a great afternoon. We'll talk to you later.